So today we are going to be going over our last set of calculations for our thermochemistry unit. And this is called molar enthalpies of formation. So we're actually going to be using our data booklet for all this here because we do have, if you remember page, I think it's 4 and 5, it has stuff called molar enthalpies of formation in it. So I'm just going to show you what that looks like here just so you're not surprised. So you guys seen these before, right? So we have standard molar enthalpies of formation. So now we're actually going to use this area of our data booklet for this unit. So what we have here, standard molar enthalpies of formation, so is designated this, so delta FHM with not, so remember that means standard, change in enthalpy, F for formation, and that little M is just molar. All right, so breaking out all of those words, but it kind of means the same thing. We can just say, sorry, delta H, right? Molar enthalpies formation if we want. But anyway, what this is the change in energy, specifically potential energy, that occurs when 1 mole of a compound is formed directly from its elements. So because we have formation, right, these are all about formation reactions. And remember, if you reverse it, reverse a formation, you have a decomposition. Reaction. So technically that table, you can just take all of these values. This is the formation of like aluminum oxide, but the decomposition, we just take this negative, turn it to a positive, and it represents the exact same thing. So technically this table operates as a standard molar enthalpies of formation and standard molar enthalpies of decomposition. All right, so as we're reading questions, just keep this in mind that if we reverse formation reactions, you have a decomposition reaction. So that's why our table can actually have more useful information than anything else, because we have both of those processes. Now, of course, with these here, we need to use a reference state, mostly because this is going to show up a lot as we go through chemistry, but when you're trying to analyze something, you kind of need like a base reference point. So for us, our reference point is going to be the potential energy of elements, and we're going to define it as 0 kilojoules. Because, well, you cannot take an element and directly measure its potential energy. That is why we're just going to assume if we have an element, that is just going to be the base. Therefore, when we add two elements together for the formation, if it's exothermic, then, well, it's exothermic. If it's endothermic, it'll be endothermic. And that is just our base unit. So our equation that we are going to use, now this is a bit of a doozy, and I know it looks big, but it's not that bad when we actually break it down, because we know what this means. Delta RH with the little circle above, not. This means that the enthalpy change for a reaction under standard conditions is equal to, remember, sigma here means the sum of the number of moles. Now, I know we don't have the multiplication here, but it is the number of moles multiplied by the molar enthalpy of formation of the products minus the same thing, the sum of the number of moles times the molar enthalpy of formation of our reactants, right? And this is all worded out right here. Now, honestly, using this equation is going to get a little cumbersome because we're going to have big equations right here, but as long as we have the balanced chemical equations, we'll be fine because we have the coefficients. And the number of moles right here for both of these here are going to be molar coefficients from our balanced chemical equation. So that's why, well, balancing is obviously going to be important. And that is why when we look at step 1, to solve these here, we need to write our balanced chemical equation first. All right? And that is going to be key, because if we know up here, and I just told you that the number of moles are going to be from the molar coefficients, we have to make sure we have the correct molar coefficients. Step number 2, we are going to reference the molar enthalpies of formation of all the reactants and the products, and we're going to have to write them down. And if we see an element, it is 0. And then finally, use the above equation to solve. So in theory, like, all these steps aren't that bad. Balanced chemical equation, figure out the numbers, plug them into the equation. So let's see how it works. Now our first example on the next page is going to be, it's a made up example, obviously, because there's no compound W, compound X, compound Y, or compound Z. Although I think compound W is for wort treatment. So yes, there is compound W, but not in chemistry. So what we have right here is determine the enthalpy for the reaction in this general equation. So we have X plus 3Y produces 2Z plus 2W, and we have an unknown enthalpy. So our equation, we know. Now this is going to get rather, I'm probably going to end up filling out the space and having to go down a little more, but that is perfectly okay. Now in this one right here, they're giving us the standard molar enthalpies of formation, so we don't need to look at our data booklet because it's given. So we write an equation. Delta RH naught, you don't really need to write the R or the naught, it just helps, equals to the sum of, we go number of moles multiplied by the molar enthalpies of formation.
Good afternoon, everyone.
Of our, what do we have right here, products, minus, same thing, the sum of the number of moles times the molar enthalpies of formation of our reactants. I know there's a lot of symbols and everything like that going on here, but once again, practice will make this a little easier because there's symbols, there's numbers, there's everything. But once you kind of write this out, and then it's just kind of making sure separate, we have our reactants over here and our products here. So it's always products first, because remember where we're doing the change in, delta is final minus initial. So our final is always over here, right? It's our products, and our initial was our reactants. So we are going to start filling in our numbers or start to clean this up a little bit. So the sum of, what I like to do is separating reactants and products, I like to use square brackets and then everything that goes in here. So for my products, I have 2Z and 2W. So I'm going to go 2 times the molar enthalpy of formation of Z, compound Z, and I'm going to add this, because it's the sum of, 2 times the molar enthalpy of formation of W, and brackets. So that's all my products. Minus my reactants, I have 1 times the molar enthalpy of formation of X, and then plus 3 times the molar enthalpy of formation of Y. That's just how I like to organize it. Now you're going to find your own little cheats and stuff like that to work, but whatever works. Now what I'm going to do is start filling in these right here, because these values are molar enthalpies of formation. And that's what we're going to get. So let's do it. Change in enthalpy is equal to, I'm going to do square brackets again, so I got 2 times the molar enthalpy for Z is right here, negative 75.8, negative 75.8 kilojoules. Now I know it's supposed to be in kilojoules per mole, but technically it's moles here. I forgot to put that in moles, but I just like to, because we're dealing with 1 moles, I just write kilojoules. Plus 2, molar enthalpy for W is right here, a positive 24.2. Now definitely be careful about your signs here, because you don't want to mix these up inside of this equation, right? You'll end up messing everything up. Next, same thing, I'm on to my reactants, so square brackets, keep that in there. I'm going to have 1 times the molar information of X is right here, 50.50, positive 50.5, and then plus 3 times Y, Y is right here at 30.4, specifically 3 times a positive 30.4 kilojoules, and I kind of ran out of space there. Kilojoules. So now we just math all of this out. So when we, now I just need to make a little more space down here, so just give me 1 second. Okay, that looks better. So we have delta RH is equal to, now the sum of all the products right here, when you do 2 times negative 75.8 plus 2 times a positive 24.2, we're left with an overall of negative 103.2 kilojoules. This is for our products minus our reactants. When you're done this one, you should get a positive 141.7 kilojoules. And then if we go plug this into our calculator, we get delta RH is equal to an overall of negative 244.9 kilojoules. And that is plugging all that into our equation, and of course, hopefully everything works out. So I know that was just kind of a lot right there. So if you are kind of watching this at home, you can pause the video, make sure you clear all this up. If you're still writing this down, fine, like just kind of pause the video, but I know if we're watching this in class, it's going to be a little hard to pause the video. But anyway, the Chromebooks are booked out, so if you do need to go back and review this, please do. But I'm just going to go on to example 2 as well, just so we can actually see what to do when we need to use our data booklets and we're not given the molar enthalpies of formation here inside of the question. Because sometimes if you are given, I don't want to say fake or just theoretical molecules like this, the molar enthalpies of formation are given to you, but other than that, you are expected to go to your data booklet and reference all of the things here. And it can get tedious trying to find them, but you do need to make sure to pay attention to states of matter and everything like that. So, with that in mind, let's look at example 2. Alright, so question 2 reads, methane is burned in furnaces and some power plants. What is a standard molar enthalpy of combustion of methane? So assuming water vapor is a product. Now, this is more of a typical type of question that you're going to see, is because first of all, you notice that there's no reaction, so you need to come up with the reaction yourself, right? So let's start with that. My reaction, we have methane, so that's CH4, which is a gas. It reacts with oxygen, O2, which is also a gas. Produces CO2, which is a gas, and then finally assume that water vapor. Now normally that won't always be the case, it won't say that, but you need to know, assume it's an open system, therefore water vapor. So we got H2O, gas. And of course we balance, so we need a 2 in front of that and a 2 in front of that, and it should be completely balanced. Now, this is when we try to figure out, well, we will need standard molar enthalpy of combustion, not just enthalpy change, but we'll get to that towards the end. So we start with, we have our equation, now we do our, balance equation, now we do our our math equation. So we know the change in enthalpy is going to equal the sum of the number of moles multiplied by the molar enthalpy of formation of our products. And we subtract this from the sum of the number of moles times our molar enthalpy of formation of our reactants. So now we start expanding. We have our products, we have 1 CO2 and 2 H2O. Now remember, it's H2O gas, and we'll pay attention to that now in a second. So we have delta H is equal to, now once again, I just like using square brackets to keep everything in there. So we have 1 times the molar enthalpy of formation of CO2. And we're going to add this to 2 times the molar enthalpy of formation of H2O. Those are my products. My reactants. I am going to take 1 times the molar enthalpy of formation of methane. I'm going to add this to 2 times the molar enthalpy of formation of oxygen. Now, at this point in time, if you remember back a while back, or just a few minutes ago, or whatever, let me go back to it, we have reference state, a reference point which potential energy of elements is 0 kilojoules. So, if you recognize, if you recognize that you have an element, in this case, overshot it, like oxygen, what you can do is scratch this out, 0 kilojoules, right? And just write in 0 kilojoules because you know that it's not going to do anything. So you can technically leave this out altogether. All right, now we got to start putting in numbers. So you go delta H is equal to square brackets. Now we know it's 1 mole times. We got to look up the molar enthalpy formation of carbon dioxide. So we go to our data booklet and we find carbon dioxide. So let me make this a little bigger here. And we go down and we'll notice carbon dioxide is right here, and the molar enthalpy of carbon dioxide is negative 393.5 kilojoules of energy. So I go back to my notes and write in negative 393.5 kilojoules plus. Now I need to look up the molar enthalpy formation of water. But remember, I specifically highlighted, we highlighted water as a gas because when we look at our data booklet, water shows up as water liquid and water vapor, and they both have different molar enthalpies of formation. So you have to make sure you choose the right water. So that's why I stress the whole thing about open system and closed system combustion reactions when we did that lesson. Actually, that was the first lesson in thermochemistry. So anyway, we have 2 times negative 241.8. So we're going to write that in here. Plus 2 times negative 241.8 kilojoules and brackets and my square brackets. So these are all my products minus my reactants. Well, I get to ignore oxygen because it's not there. I just need to look up methane, which I'm going to scroll up, look in the M's. We see methanol. Methane is right here in negative 74.6. So it's 1 times a negative 74.6 kilojoules and M brackets. So I simplify, right? Now you can do this in the one shot if you want to, which that's what I'm going to do. So basically when we simplify all this, we get a negative 802.5 kilojoules. And that is the change in enthalpy for that reaction. You'll notice that we need molar enthalpy, however, and that's why I circled it right here. So our last step, if it asks for molar enthalpy, we need to give it. So molar enthalpy is equal to the change in enthalpy over number of moles. Now the change in enthalpy we just figured out. The number of moles of methane, we need to look at our balanced chemical equation again, is just, luckily, it's 1 mole. So we go 1 mole, and we have the change in enthalpy, or the molar enthalpy, sorry, for the combustion of methane is negative 802.5 kilojoules per mole. So that is how we find molar enthalpy, or just change in enthalpy from balanced chemical equations. Now, normally the big questions we get from this is like, how do I know when I need to use this equation? Well, you're gonna know that you need to use that equation if no enthalpy change is given to you whatsoever. So if you read a question and there's no molar enthalpy and there's no enthalpy change for a reaction, you need to use this equation to solve. That will always be the case. So like if you switch over now and look at example 3, same thing. What is the standard molar enthalpy of combustion of ethanol, C2, H5OH, in an open system? So you'll notice that it's just asking for the standard molar enthalpy of combustion. It's not giving us molar enthalpy. It's not giving us any information whatsoever. So you'll notice that you need to use this equation when you have one of these. So the answer for this when you do it, once again, after you're done watching this video, go back and try. Just write this answer down somewhere. So when you go back, you know if you did it right. So you should get negative 1,234.8 kilojoules per mole. Now the other type that you can get is sometimes the molar enthalpy will be given to you, or the enthalpy change will be given to you, but it's going to ask you to solve for the molar heat or the molar enthalpy formation of something that isn't in your data booklet. So for example, methyl bromide, and this is example 4. Right? It says in laboratory conditions, this is a reaction. So we have methyl bromide, CH3Br plus hydrogen produces methane and hydrogen bromide gas. Now you'll notice hydrogen won't be here because it's an element, but when we look at methane, CH4, it's in our data booklet, CH4, we just solved for it. Same thing with our HBr, hydrogen bromide, it will be in our data booklet as well. Right, so if we scroll down, we see hydrogen bromide right here, HBr, and we have a value with it. If you look in the M's, right, manganese carbonate and, magnesium carbonate, magnesium chloride, and the other M's, we have our here. I'm not going to list out all of them, but we know methyl bromide is not there. That is because you're going to use algebra. When you write out your equation, this is your unknown. This is what you're solving for, and this is your unknown, and you're solving for it. All right, so I want you to try this one once again on your own. Once you guys get, once you write everything out and try it, and you should get the molar enthalpy of formation of HBr should equal to negative 184.5 kilojoules per mole. Now, with this particular answer, I do have it worked out step by step on the answer key that's posted up on Google Classroom. So if you try this one and you can't get the answer, just hop on Google Classroom and have a look at the algebra that I done, and I have everything set up as well, right? Now, the reason we're going to do this, and I'm going to step over the diploma example, and I want you guys to do that too. Go back and try it on your own time. Same thing, just have a look if you can get the right answer or not. And I just want to jump into putting all this together. Now, we kind of done this with Hess's law, and I kind of mentioned that if you're in class, I gave out the sheets with it was the hydrogen example, and if you watched a video, I too kind of highlighted how to tie stuff together. Now, sometimes you're going to be given something like you're going to be tying calorimetry together with molar enthalpies of formation, or even calorimetry with Hess's law and enthalpy change. But anyway, these are all our equations right here. Now, calorimetry just kind of takes everything, but technically we only have 1, 2, 3 different equations. That's it. And that's just Q is equal to MC delta T, delta H is equal to NH, and our molar enthalpies of formation. Because Hess's law, just adding them up, that's just what thermochemistry is, and calorimetry combines the first two. But I'm going to go through the first example with you, and then I will kind of let you guys see if you can get the second example. And then, of course, the key to this is you need to be able to practice as much as possible, because these are the difficult questions. Now, what we have is, what mass of octane is completely burned during the heating of 20 liters of aqueous ethylene glycol automobile coolant from negative 10 degrees to 70 degrees Celsius? And it says the volumetric capacity of aqueous ethylene glycol is 3.7 kilojoules per liter degree Celsius. Now, right away you can tell that this is basically a different type of calorimetry question. So we know that we need to use our calorimetry equation at some point. However, you will notice that delta H is missing from this equation. And if you remember with calorimetry, when it's asking for what mass, just kind of jumping ahead, we know that it's of ethylene glycol, what mass of octane. So in our equation, NH is equal to MC delta T. If octane is burning, that means we need to solve for number of moles at some point. So rearranging, we need to find molar enthalpy. All right? So that's just kind of looking ahead. But anyway, the fact that, and I mentioned this earlier, is that if we have a balanced chemical equation and we don't have our delta H, solve for it. Use molar enthalpies formation to solve for it. So that's the first thing I'm going to do. And I'm just going to figure out what delta H is, and therefore probably H. So let's do it. We got delta RH is equal to the sum of the number of moles times the molar enthalpies of formation of our products. I'm just going to write P, all right? We can shorthand stuff. Minus the sum of the number of moles times the molar enthalpy of formation of our reactants. So our reactants, I'm just going to pay attention to, we have gaseous water here in CO2. So we're going to add this up, take into account, once again, square brackets if you want to use it. I like doing that. But I'm going to take, we have 16 CO2s, so we're going to go 16 times molar enthalpy of formation of CO2. And we're going to add this to 18 times the molar enthalpy of formation of H2O. That's my products, my reactants. I'm going to take 2 times the molar enthalpy of formation of octane, and that is it. Now, the reason for that, remember, element, and the molar enthalpy formation is 0. So, referencing our data booklet next, or the next page, CO2 and H2O we used on the last page, so I'm not going to go back to the data booklet for this one right here. For carbon dioxide on the last page, or the data booklet, we have a negative 393.5 kilojoules. And for our water, gaseous water, remember, not liquid, was negative 241.8 kilojoules minus, now our octane is 2, go to our data booklet, and we find octane is right here, and it's a negative 250.1 kilojoules. I know it's kilojoules per mole, but once again, I'm just leaving that out because it's 2 moles. I just wouldn't have enough space to write moles and everything like that. Now when we solve, is equal to negative 1014.8.2 kilojoules. So that is a change in enthalpy. Now, just like the other ones, it's very handy to know change in enthalpy, but not only that, molar enthalpy specifically of octane. So let's figure it out as well, because we've done our previous examples, like example 2 and 3 was always like, or example 2 was molar enthalpy, example 1 was just enthalpy change on the previous page, and 3 was even molar enthalpy as well. But I know how useful molar enthalpy is, so just kind of on the side here, if we want, we can go, all right, molar enthalpy is equal to the change in enthalpy, and this is for octane, right? Because we know we're going to need the mass of octane at some point, so we should be finding the molar enthalpy of octane, because I know I'm using my calorimetry equation, so I should be finding the molar enthalpy of octane, right, if I want the mass of octane. So I'm going to take this, divide by that, and from our balanced chemical equation, we got 10148.2 kilojoules divided by our 2 moles of octane from our balanced chemical equation, and we are left with negative 5074.1 kilojoules per mole. Sweet. So that's kind of just getting our first problem out of the way, is that we wanted the change in enthalpy for the reaction because it wasn't provided, and because we know we need to solve for the mass of octane, we need the molar enthalpy. And that's why these questions kind of get a little more challenging, because you need to be able to think ahead and just piece together the information that you know you're going to need and then go out and find it. All right? Now, our next step is once we have our molar enthalpy, same thing. So I'm just going to scroll up for a second and just look at the information we're given. Like I said, we can tell because we have polyethylene or ethylene glycol. A temperature is going up, we're given a specific heat capacity, and we're given the volume. So we know we're doing a calorimetry question, right? We know that NH is equal to negative MC delta T. We know this. So that's why next, when we look at it, we know we have MC delta T, and we did all that work to find H. And just by looking at the variables, we're actually almost done the question, right? So I'm just going to go to a blank page because I just kind of ran out of room here. So our next step, so let me adjust this. So our next step is find N. We're going to use this, right? So remember, this is for my system, and this is for my surroundings. So our system equals octane, because that is the combustion. Our surroundings, I'm just going to write SUR, S-U-R-R. This is the ethylene glycol. So that means NH is for octane. Negative MC delta T is for our ethylene glycol. right? So let's work this out. We got NH. Now I'm just going to rearrange and solve for N, because I know I'm going to need to solve for that. So N is equal to, now negative, the mass of ethylene glycol was 20 liters. Specific heat capacity, sorry about that, I'm recording this in the classroom here now. So we have the volume of ethylene glycol was 20 liters. Specific heat capacity from the question was 3.7 kilojoules per liter degrees Celsius. And the change in temperature was 70 degrees Celsius minus our negative 10 degrees Celsius, all over our molar enthalpy of 5074.1 kilojoules per mole. And we're left with N is equal to 1.1667 moles. Now finally, I know this seems like a lot, but we are actually just one more step away, is that we know as soon as we get number of moles, we get mass. It's equal to number of moles times our molar mass, and we got our 1.1667 moles times our molar mass of 114.26 grams per mole. Remember, octane is C8H16, and we are left with 133 grams. That is a lot. But that's just to kind of give you an idea on how all of this can be combined into one massive question. So here we had a combination of calorimetry and molar enthalpy of formation. Like I said earlier, the one that we gave in class, the hydrogen example, that was also I highlighted in the video for Hess's Law, or if you're in class you had the handout there. That was having Hess's Law and changes in enthalpy linked together. So all these kind of go hand in hand, and you can get these things linking together. We can get Hess's Law and calorimetry linking together. We can get molar enthalpies of formation and calorimetry linked together. We can get molar enthalpies of formation and just change in enthalpy linked together as well, right? So just make sure that if you're not given your equation or your change in enthalpy, write out your equation and use molar enthalpies of formation. So that just brings me to the last question there. And then I'll let you guys try to get some work on these here. And that is on the next page. So this one, same thing, you're going to notice there's no equation given. Right? It says the respiration of glucose is chemically similar to a complete combustion reaction but produces liquid water. Calculate the change in temperature of a body composed of 65 kilograms of water during a respiration of 18.5 grams of glucose. Now this one right here, basically the human body is just a giant calorimeter. So this 65 kilograms of water is what is our body made of, okay? So your first step is you need to find the molar enthalpy of glucose. Once you get that, plug in your calorimetry equation and solve for delta T. You should get from this one right here, delta T is equal to a positive 1.06 degrees Celsius when you get it, all right? Now in the answer key, I have this done up. Step by step. So you guys can definitely have a look at that, but please try it. Make sure to work through this one, work through your workbook questions, because some of the workbook questions are a little easier when it comes to this, but please make sure you give these a try. And if you have any questions, either review this video again or fire me up an email and I'll try to answer things right away. All right? So that is it for today's lesson. Please make sure to make good use of your time and practice this as much as possible. And once again, the Chromebooks are kind of out, so if you're watching this in class, hopefully the Chromebooks are booked so you can pick these up and review this lesson. If you're watching at home, well, you can just review it at your leisure. All right, so that is it for today. I'll see you guys later.